Thank you. Sure, thanks. So first off, I would like to thank Pinaki and Arnab for inviting me. It's nice to be back in Chennai after 24 years, and I'm enjoying all the glorious comfort food per unit time as humanly possible. So it's after lunch. I know you all must be feeling sleepy. So I decided no glasses, no active matter, no resetting. It's going to be a bunch of movies. But what kind of movies? We all go around in circles, okay? So simple kind of movies. But either you will come out hallucinating after, yeah, either you will come out hallucinating or hypnotized, okay? So this work is just fresh off the lab. It's still not written up, and I'm still trying to think of the best way to present it. So this is the first time I'm presenting these results. So this is one way of presenting it. But if you have any feedback, I would be very interested. I would like to start off by explaining what the experiment was. It's a very simple experiment. Think of a tank of water, and we are exciting waves on one end, and we have a vortex, and it's an experiment that tries to study the scattering of these waves off this vortex. But it has connections to the famous Aharonov-Bohm effect we study in quantum mechanics textbooks. And so I'm going to try to cast the results in that language. And there is a very rich history of these connections between hydrodynamics and electrodynamics that go all the way back to the founding fathers, to Maxwell, who used electrodynamics to advance his understanding of fluid dynamics, and Hermann von Helmholtz, who went the other way. He used his knowledge of he tried to improve his knowledge of hydrodynamics, especially vorticity, using electrodynamics. Okay? So this is also the first time in my career that theory, experiment, and numerics are matching. So I couldn't believe it when it happened, so we had to go and cross-check everything. So either we have done something trivial or we got very lucky. Okay, so before I proceed, let me tell you a bit about what we do. So my training was in turbulence, that graveyard of theories where you never get the satisfaction of having solved something. So you can understand why I'm excited about this working out. But slowly I'm getting into this topic on topological fluid dynamics. Another topic is, as I was quoting my good friend Shmuel Rubinstein earlier today, he said when all else fails, there's always biology. So we do a bit of quantitative life sciences, and we are currently working on the predator-prey interactions between redback spiders and ants. And then something I started after I moved to Okinawa, which is fluctuations, applying statistical physics concepts to energy and sustainability to understand fluctuations in renewable energy sources. And then something I took up during my postdoc days at Los Alamos, which was granular media. I'm winding up that work on frictional granular jamming. I'm thinking of some tabletop experiments in triboelectrically charged granular matter, but it's a very difficult problem. And then there is an odd assortment of questions that don't get classified, which are just left aside. Okay? So the dramatis personae are, Jonas Roning is a postdoc with me at OIST. He did the theory and numerics for the work I will discuss. Aditya Singh is a PhD student. He did the experiments. Andres Concha is a close friend of mine. We both were postdocs at Harvard, and that is when, about 10 or 11 years ago, was when we first started cooking up this problem. But what I'm discussing today is not the problem we cooked up. So the story is nonlinear. So he contributed to both theory and experiment, and Luisa Angeluta Bauer is a collaborator from University of Oslo. She contributed to theory and numerics, and I was settled between experiments and numerics. So it was a division of labor. So let me, for the benefit of students, I'm going to give you show you this YouTube video about how the B field works in a magnetic field works in a solenoid.
If a solenoid carries a current, it produces a magnetic field that is parallel to the axis and close to constant inside the solenoid. The magnitude of the magnetic field is proportional to the current and to the number of turns of the solenoid, divided by its length. Outside the solenoid, the magnetic field is very small, as can be seen from the small magnitude of the readings, which is represented by the wide spacing of field lines in the diagram.
Okay, so that's the conceptual background you need to understand how a solenoid works. The last bit that the speaker mentioned, that there's a slight leakage of the magnetic field outside of the solenoid, is relevant in part to what I'm about to explain. So when we study the forces exerted on a charge in classical electrodynamics, we basically work with this equation for the Lorentz force from 1895. And in this classical picture, the fields are the primary drivers of force. They take the center stage. Okay? Potentials are always considered a mathematical convenience. They lack any physical significance because, as we all know, potential can be defined up to within an additive constant, right? But this view changes when we go from the classical to the quantum realm, where particles can also behave like waves, and waves, as we know, can have a phase as well. Therefore, one must consider not just the deflection of particles by these external forces, but also the change in their phases. Okay? But the E and B fields are not the primary physical quantities to study phase change. Rather, it's the scalar and vector potentials from which they are derived. So this became the conundrum, so to speak, when Aharonov and Bohm and few years prior to them, Sida and Ehrenberg proposed this thought experiment where they said that you can have measurable consequences of the vector potential, the magnetic vector potential. I'll come to that in the next slide. So phase is an argument of a complex number of unit modulus associated with the cyclic evolution of a physical system, specifically of a physical parameter that leads to a net change in the phase that depends upon the path geometry that the particle takes. So if the potential changes the system topology, this induces phase shifts which we call geometric phases. The most elementary form we study in high school laboratories is the Newton's rings. That is the most elementary form of a geometric phase we study in physics labs. Now, when we move from the classical to the quantum picture, let's imagine we have a charged particle under external influence going around a solenoid. We have the kinetic energy operator and the time-dependent Schrodinger equation. When we evolve this equation on the wave function psi, it picks up the this phase which has, so the wave function has no contribution coming from the vector potential A, but the phase does pick up a contribution from the vector potential. Okay? And this is basically coming from phi sub b. So basically this vector potential is encapsulating the total magnetic flux enclosed within that cycle. So the Aharonov-Bohm effect, when we study it, comes about through this picture. So if you imagine that you have a, So if you imagine you have a bunch of electron beams going past a solenoid here, where the magnetic field is 0 outside of the solenoid, but the vector potential is not, then the path taken by these electron beams is going to give you an interference fringes. Of course, if there is no, if the solenoid is shut off and the vector potential is 0 and the magnetic field is 0, even then you will get interference fringes. But when you turn on the magnetic field, which is 0 outside of the solenoid, but the vector potential is not, there is a quantized phase shift in the interference fringes. And that quantized phase shift is captured by this quantity delta phi, which is q over h bar c times the enclosed magnetic flux. And this can be traced to the path difference with where you have a topological pickup here. Okay? Now, this picture differs from electromagnetism because there only the electric and magnetic fields have observable effects, right? Now, in 1980, Michael Berry and co-workers did a nice experiment, literally in a bathtub. So Michael Berry filled up a bath striking the vortex, and the vortex itself is like the solenoid. And you can notice that when the wavefronts strike the vortex, they develop a dislocation. And this can be explained through a dislocation parameter, alpha, which goes as q over h times phi sub b in the quantum case. And it has a classical analog in, which shows up. Why isn't it coming up? Okay. So in the fluid analog of this quantum effect, you basically draw a mathematical correspondence where the vector potential is like the fluid velocity, and the curl of the velocity, which is the vorticity, is like the magnetic field, which is the curl of the vector potential. And you have the surface waves that are striking this vortex, and you have wavefronts that are now unobservable, and you can go between the quantum and the classical case. Here you can map the Schrodinger equation to what we call the shallow water wave equations in fluid dynamics. The math is simpler in the quantum case, which is where we did all the theoretical, sorry? Eta is the viscosity. So the math is easier to work out in the quantum case, but you get better intuition because you can see everything in the classical case. Oh, sorry. No, eta is not the viscosity. It's basically the surface height, the surface deformation. This is the trouble of having done turbulence all your life and then suddenly shifting to shallow water wave equations. Sorry. Okay. Now, that is what Berry had done, and there have been many nice works following up on Berry's beautiful experiment. What we decided to do was study it with standing waves. I'll tell you the truth, that is not what we originally decided to do. We also started with traveling waves, but we were having some difficulty with the wave maker. So I told Aditya, our student, why don't you, we have these acoustic transducers in the lab, why don't you just stick them to an acrylic plate, set them on the surface of water, and excite waves and set up standing waves, so that we can calibrate our experiment. But when he did that, he saw something, and we tried to remove it, and then Jonas said, I see it in the simulations too. And that is where the story went off at a tangent, okay? So what happens is, when you have standing waves, you can decompose them into two traveling waves coming in from opposite directions, okay? And these are linear equations. We simply add up the traveling wave solutions. But counterintuitively, the dislocations do not just simply cancel. Instead, you get what I like to refer to as the BMW propeller going around in circles. So what you see is basically a far field structure for this interference pattern, which leads to the nodal lines. Nodes, as we study in wave mechanics, is basically where the phase goes to 0, right? So you have the wave function for the traveling waves coming in from the right, going past this vortex. And then you see the dislocation over there. And you have the waves coming in from the left. The picture is just inverted. And if you add them both, you get this instead. You have standing waves, but you have these rotating lines with 0 phase that run exactly in the opposite direction to which the vortex is going in. So if the vortex is circulating clockwise, the nodal lines go counterclockwise. And this comes about, you can show through some mathematics, is basically there is this phase term and then the rest of the wave function. In this phase term, you have these 3 terms. The first and the third term are time independent, but you have a time dependent term here with a negative sign. And that is what is causing the nodal lines to rotate in the opposite direction. So it's as simple as that. And then if you start changing this dislocation parameter that I mentioned, it determines the number of nodal lines you get. So when alpha equals 1, you expect to see 2 arms of the nodal line about the vortex, which is at the center. If you move slightly past 1.25, they split into 2 pairs, ever so slightly. And as you approach 2, you get 2 pairs of nodal lines. You go to 3, you get 3 pairs, so on and so forth. Okay? So to tell you about how we did the simulations, it's a very simple simulation that you can run on a laptop on Mathematica. So it's a standard wave equation with time derivative replaced by the material derivative. The velocity is said to be that of the Rankine vortex by Fiat. The Rankine vortex is basically a vortex with a solid core, okay, so that you have an irrotational vortex. The waves are produced by adding an oscillating source term, and we have periodic boundaries with a damping term like a damped harmonic oscillator, so that we can avoid recirculation of the waves. And then we do the time integration using the 4th order Runge-Kutta scheme and space using Fourier transforms. So as I said, this is a simple and minimalist numerical scheme. Run it on Mathematica on a laptop, nothing fancy. I'm not lazy, I'm just an effort minimalist. Okay? So now I'll come to the results. So on the top you see the traveling wave solution, and the bottom you see the standing wave solution. So the top one is what Michael Berry had worked out initially. So the traveling waves have dislocations in the phase over here, and I'm plotting both the amplitude and the phase for you. The nodal lines are acting as domain walls. You can see it sort of here. But in the standing wave case, you get these propellers, and you can capture them more clearly in the phase plot. Okay? Now these lines, as I said, move in the direction opposite to the flow for the reason I showed you in the previous slide here, because there's a negative sign here. And now what you notice is this is a quantization that is happening, but it has nothing to do with quantum mechanics. This happens in both classical and quantum mechanics. But phase is not an observable in quantum mechanics. That was the original reason why Michael Berry did the bathtub experiment in the first place, because it can be observed in the classical analog. Right? But so phase is unobservable in the classical case, so that is why we are able to observe it here. And then we move from, so this is for alpha equals minus 1.5, but if we go to minus 1.1 and minus half, all the results are borne out. You see the splitting of the pairs, and then they become, so you can sort of make out here just about the horizontal line. It splits into two pairs and then goes back to a single pair. So basically the quantization is closest to the nearest integer of alpha. This is at 2.5 and at 3. So as you increase, yeah. Sorry?
I'm still not sure what you mean by observing phase here. I'm not getting an intuitive idea of how do you observe phase.
You can take you can set a reference phase as this is the 0, and from there relative to it you can ask how much of how much has the wavefront shifted relative to it. So now coming to the experiments. So this is a photo of the experiments. We have a tank about 1 meter in length and half a meter in width, and we fill it with water to about 20 centimeters in depth, and we drain. We have basically a drain at the bottom of the tank to generate a vortex. That is basically draining the water using a water pump, so we can control the strength of the flow rate or the circulation as a result by controlling the power of the water pump. Through that, we can either have a tubeless or a vortex with a tube. In this case, all the experiments were for a tubeless vortex. And then these are the these two are the transducers on one side. Though you see two more transducers on the other side. They are fixed to an acrylic plate, and these are piezo transducers. So they are connected to a function generator through an amplifier. So they are sending out acoustic waves. Now the acrylic plate acts like a speaker. So it gives you uniform and homogeneous, spatially homogeneous acoustic excitation. So it basically moves the acrylic plate up and down to generate the waves, and the standing waves are generated in between. Okay? And below this tank, we have a light source, a diffuse light source with a Gaussian filter above over here. And you don't see it, but I can move this photo. That is the camera with which we do the imaging. So it is a bit of a, it's a bit difficult to get Gaussian diffusers of that size. Those of you who do experiments, you will know that if you were to purchase a Gaussian diffuser of about 5 centimeters by 5 centimeters from Thor Labs, it will cost you about a few $100s. So we got this Gaussian diffuser by breaking apart one of these monitors. You get they are very high quality Gaussian diffusers and Fresnel lenses. So you hack your computer or your monitor, you get a lot of experimental parts. Now for to calculate the vorticity and the velocity field, we do it through particle imaging velocimetry. So you see a pipe here that's basically sending a laser beam down here, and we pass it through a cylindrical lens to to illuminate the surface, and we have tracer particles on it. And Using that, we can track the tracer particles to pull out the vortex, the velocity field around the vortex, from which we can pull out the vorticity. And once we have that, we can then do the experiments after calibrations to look at the amplitude and the phase after post-processing of the images. And this is at alpha equals 0.68, so you don't see anything yet. This is actually traveling wave experiment. But you come to alpha equals 0.5. Once the standing waves are set up, they're in the process of getting set up, you start seeing that propeller. And then you move to close to alpha equals 0.9, and you can see the propeller even more clearly. One 1.1, you start seeing a figment of the pair splitting ever so slightly, just for a moment around the horizontal when the propeller crosses the horizontal. But once you reach 2.1, you can see two pairs of propellers. So I'll show you static images where it will be more clearer, hopefully, but you can sort of make out. So here we should have 3 pairs, but we couldn't do a good job. We are still working on this part to get it up to 3 pairs. But to give you a better idea, you see the wavefront dislocations here. This is at alpha equals 0.5, and that is the line at alpha equals 0.9. Once we get to 1.1, you get 2 pairs here, and at 1.9, the angle between those pairs has increased.
Can you just remind me what alpha was?
Sorry. Alpha is basically the dislocation parameter, which is the circulation divided by the group velocity. So we are coming up with a dimensionless parameter that is linking quantity coming from the vortex to the quantity coming from the waves.
And you can control that precisely.
Not control, but we can. So our controls are basically the frequency of the waves, and therefore the group velocity to some extent, and we can control the flow rate of the pump, through which we can control the vorticity and therefore the circulation. But we can't say I want alpha equals 2 and tune them, but we can vary these two and see, okay, how close do we get to alpha. So to summarize, what I have described is basically a classical analog of the Aharonov-Bohm effect, which is well known in the hydrodynamic context. And we have studied the same using standing waves instead of traveling waves, and that gives rise to this cyclic interference pattern with rotating nodal lines. These nodal lines arise in quantized pairs proportional to the nearest integral value of the dislocation parameter, and they always rotate with a sense opposite to that of the vortex or the solenoid if we are working in the quantum mechanical case. And they should arise in both the quantum and the classical cases, because we solved the problem theoretically in the quantum case, but we measured it in the classical case, right? Oops. The standard quantum Aharonov-Bohm phase shift is actually routinely used these days in certain interferometric measurements. So, but we know that the rotating nodal lines are more sensitive than the standard quantum Aharonov traveling wave case. So we are currently exploring if there are any potential applications of this more sensitive technique. So this is the summary of what I have described. I would like to share a bit about where do we want to head from here. Usually I'm known to do standalone experiments. I do one and then go off like a bunny rabbit and jump into a totally different field. So where we want to go next is look at classical analogs of other quantum geometric phases. So there is actually a family of these. The Aharonov-Kasher effect, which is the dual of the Aharonov-Bohm effect. In the Aharonov-Bohm effect, you have electron waves striking a solenoid. In the Aharonov-Kasher effect, you have a magnetic dipole in an electric field. Then the Aharonov-Anandan effect, which is considered the superset. So the Aharonov-Bohm and the Aharonov-Kasher effect are special cases of the Aharonov-Anandan effect. And Anandan, it turns out, was he's my academic sibling. He got a PhD from the University of Pittsburgh, but before I was born. And then there is the Aharonov-Carney effect, which considers the principle of equivalence between real and inertial forces, the potentials of real and inertial forces and their consequences. And then we want to go into collective Aharonov-Bohm phases. So this would be trying to create a vortex crystal So in superconductivity, when you have a supercurrent striking the Abrikosov lattice of magnetic flux tubes, the solution we know is what we call the Hofstadter butterfly, right? So if we did create a vortex lattice in a tank and we sent in these waves, what do we expect to see? I mean, we are not going to see the Hofstadter lattice, but what are we going to see? And then look at some exotic cases like hydrodynamic lensing, cloaking metamaterials. So here is an example where Jonas has created a Fresnel lens configuration for the vortices, and he's looking at how the interference fringes get focused as you change the curvature and the number of vortices in their sense. So that is where we are right now. It's very early days. So I'll stop there. Thank you, and take any questions, rotten eggs, tomatoes, etc. Thank you. Oh, yeah.
I think the classical analog AB effect is only valid for the in-biscuit limit.
Yes.
So that if the viscosity exists, what happen only to dispersion suppress the such effect, or
No, dissipation actually aids us. Yes, because it allows us to design experiments with waves in the linear regime. All these, the nonlinear waves is an exotic topic in itself in hydrodynamics, but we are working with the simplest form of linear waves. I mean, another reason why theory, experiment, and numerics work is everything is linear here.
okay.
But it is still out of equilibrium, so it is part of the topic of this conference.
One of the things, the equation, the shallow water equation, looks like a lot of other wave equations.
Yes.
in mathematics.
Yes.
For instance, those created by this highly fashionable non-reciprocal,
Sorry?
highly fashionable non-reciprocal those look quite like this.
Yes.
Except that the U field is sort of self-generated and not external.
Yes.
So many of these should be observable in those kinds of systems.
Absolutely. So there are cosmological applications of this work as well. We haven't gone there yet, but stuff like Unruh radiation, Hawking radiation, and so on and so forth. I left you all speechless. Sorry?
In how does it relate to Unruh?
So if we, so in this vortex, if we draw the tube, if we increase the flow rate, the point that a vortex tube is created. So you're basically changing the topology physically in physical space from a genus 0 to a genus 1 object. At that time, every time a droplet is pinched off due to the Rayleigh-Plateau instability in the fluid, there are waves that go that are radiated, spherical waves that are radiated outwards. So technically, it should not be possible because the fluid is accelerating so fast, the wave should not be going out. They shouldn't be getting out of the vortex. So we don't yet understand. It may not be related in any way to Unruh radiation, but it is one possibility.
Like, do you get like your sine waves when you do it, or like,
Yeah.
do you don't have to like,
We just set up simple sine wave on a function generator at 4 hertz, 5 hertz, 10 hertz, 20 hertz, connected to an amplifier and connected to the piezo transducer. It's simple.
Hi. When you do this PIV analysis, if I understand right, like you are having a 2D sheet on which you are looking at. So now your system is intrinsically 3D. So did you, if you look at different heights, do you see that how does your result scale with the height of the channel?
Okay, so we are not doing PIV on the waves. So we have to do PIV on the vortex because we have to pull out the circulation, the vorticity and the circulation. But for the waves, we just can get away with caustics through by looking at the caustics of the wave fronts. So we don't need to do particle imaging velocimetry there.
So Anandan was Jiva Anandan.
Yes.
Yeah, yeah. So he was actually at Wilson College at Oxford.
Yes.
when I'm finished.
Oh, okay. So his PhD advisor, what's his name? He taught.
He died very young. I mean,
Oh, he's not alive? Oh, I didn't even know that.
that was a long time ago, and he was only in his 50s.
Okay. So his advisor, Ralph Z. Roskis, taught me physics education course. It's a course that every student at the University of Pittsburgh Physics and Astronomy department had to take in their first year to qualify to be teaching assistants. And Ralph Roskis was the last student of Eugene Wigner.
Okay, comments, questions? If not, let's
Thank
thank
you.
Manish.
Arigato gozaimasu.
Okay, so our next speaker is Devashish Chaudhary from IOP Bhubaneswar. We're talking about inertial impact on active.
Okay, so let me first thank the organizers. So today I'll talk about certain aspects of inertial impact on active matter. Okay, so the people who are involved in this, I mean, this is a list of collaborators and students with whom I have been working for last decade or so. This work, part of this work is done by Chitrak. This work on active polymers and inertial impact on their properties. And Manish is in the audience. He also has a poster. A lot of the work is done by Manish, all the analytical calculation for active particles in the ideal limit. And Shubhendu was a postdoc. So he had done some calculations on the many body active Brownian particles and some emergent properties, steady state properties of that. And in that project, Fernando was a collaborator in that. Okay, so before I get into the inertial impact, let me just quickly summarize what typically we do in active matter. So some of the problems at least are like motivated by active colloids, genus particles, which can use local energy, I mean utilize fuel locally and self-propel. But these particles are typically of extremely small mass, and they have inertial relaxation time which is very small, so hundreds of nanoseconds, with respect to the typical persistence time of these particles. And as a result, one can often neglect the inertial effect in those kind of systems. On the other hand, if one takes bigger particles, for example, these vibrobots, some vibrated granular materials. So you vibrate this substrate on which, because of the frictional asymmetry or something, the particle can take locally the energy, and once it drops, it can slide and stick in one direction, slide in the other direction, and then as a result, it can move. So in all those systems, of course, there is inertia, and the inertial, the relaxation time, inertial time scale, that becomes significantly large. And in certain cases can become comparable to the persistence time of the system. So whenever the persistence time and inertial timescales are comparable, we expect to see its impact on that. So, okay, so this could be one example. There could be examples of insects. There could be examples of, like, all these are active granular materials. There could be examples of larger animals, Higgs bugs, all those kind of systems in which inertia can influence their properties. So now I take a step back and look at this phenomenon of motility-induced phase separation, which today morning also people talked about, at least mentioned about. So in these overdamped systems, it was seen both in simulations and in experiments that if you have the systems driven at a high enough self-propulsion speed, so if all the active particles has high enough self-propulsion speed, these are active persistent movers, and has density which is beyond some critical density. So you can have this phase separation. So here particles repel each other, but they coagulate, they cluster together because of the self-propulsion fit and the repulsion between particles. So this is the motility-induced phase separation which was seen, which was observed for overdamped system. But what turns out is that if one increases inertia of the particles, individual particles in this system, one can go. So, for example, this particular example of this vibrobots has an inertial time scale, inertial relaxation time, which is of the order of 0.1 second, whereas the persistence time is same order, 0.4 second. So in those kind of systems, you cannot really ignore the inertial effect, and so this was one result taken from this paper. They measured something called a delay function, and the delay function was what? That each individual, this active particles has a active orientation in which they are supposed to move, and this orientation is HATU, and particles actually have some velocity. So if this is completely overdamped, this velocity, this active velocity and this orientation, they should be aligned. So this misalignment between them, so that remains up to some time scale, and this is the time scale over which it remains, and that shows this delay between these two functions. If there is no delay, these two quantities, of course, like if these were like equilibrium quantities, this should have been 0. So I am taking 2-point correlation between velocity and orientation, but this is, if this is in time t, this is in minus t. So subtracting these two out. Okay, so this says that there could be important impact on of inertia on the dynamics of these active particles, but then if one goes back to the scenario of MIPS, motility-induced phase separation, this was shown by Hartmut-Loewen's group. So what happens is that if you have this inertia, this capital M quantity here, this is the ratio of the inertial relaxation time by the persistence time. So this ratio, this one, inertial relaxation time by persistence time. So if this ratio becomes, unless it's too small means this is like 7%, unless it's not less than 7%, you can't see motility-induced phase separation. For any larger ratio of this inertial time scale, motility-induced phase separation completely disappears. So it's a many-body effect. So a phase which disappears and presence or absence of the phase depends on inertia. This behavior is, of course, like very, very unlike of whatever we know from our equilibrium physics. So in equilibrium physics, of course, all the late time properties don't depend on inertia. So they are, for example, even this thermodynamic properties, temperature, pressure, chemical potential, they are not inertia dependent. And even kinetic quantities like kinetic temperature, Tackt particle diffusivity, mobility, these quantities, asymptotic properties of them, they are independent of inertia in equilibrium systems. And of course, equilibrium phase transition does not depend on the inertial part of the Hamiltonian. This just depends on the interaction. And one just looks at the partition function from the interaction part and describes the phase transitions. So I have already shown in this active system one example that MIPS gets modified in presence of inertia. What we'll try to do in this talk is to show that what are the other possible impacts of inertia on active processes. So how these equilibrium notions are violated in active matter. Okay, so with that I come to the outline of my talk. So what I try to do is that, so this is the basic question, that how particle mass affects late time or steady state properties of active systems. That's what we will try to probe. And for that first example, I'll show active polymers, properties of active semi-flexible polymers. And I'll show that in presence of inertia, there is a re-entrance towards equilibrium-like properties. And in active Brownian particles, as I already mentioned, that this MIPS, Hartmut-Lorentz group showed that MIPS disappears if you have little bit of inertia, only 7% with respect to persistence. So I would like to ask this question, that what happens to other steady state properties even if I don't encounter phase separation. So if I keep my activity low enough, my density low enough, so that I don't encounter I showed in that phase diagram that there is a regime of motility induced phase separation. Below that there is a homogeneous isotropic kind of phase. So even in that phase, is there an impact on the packed particle dynamics of this system? And finally, we'll do some exact calculations in using ideal system of inertial active Brownian particles. Maybe I should call this active Langevin particles. Okay, so the first example. So this first example of active semi-flexible polymers was, so I'm just giving again like the over-damped motivation. Active semi-flexible polymers, people have been looking at it from, for example, from the perspective of understanding biological systems. Here there is this experiment done on actin filaments on myosin bed. So these are actin myosin molecular motors coat this this substrate on which this glass cover slip, and the actin filaments are being driven by this irreversibly attached myosin motors on the substrate. As a result, actin filaments are driven on top of it. And this was shown long back that these actin filaments undergo this instability and gets into this spiral formation, spiral dynamics on top of this molecular motor assay. So motivated by that, there are several studies, and our group also had looked at such systems. So in which one can model the length stabilized actin filaments as semi-flexible filaments. So I'll not get into the full detail of this model, but these are like bit spring models in which semi-flexibility is incorporated by giving a bending rigidity between consecutive bonds. And then there is an active force. Molecular motors try to walk on top of this actin filament, and as a result drives it in the opposite direction but tangentially. So that can be roughly modeled as a local tangential active force acting on top of this filament. And if you increase this active force beyond a point, you see this buckling instability, that the head of this filament can buckle, and after it buckles, that gets into a trap and gets into this spiral formation, and the lifetime of this spiral depends on the length of the filament. So if one increases the length, the spiral remains in this spiral phase for a very long time, and after some point, of course, it can come out of that spiral, and because there is no chiral symmetry breaking, it can go either right-handed or left-handed spiral, but it keeps on jumping between one to the other. So that happens at in the overdamped limit itself. So then we are interested to see that, okay, so one can also imagine developing this similar semi-flexible chain of active elements, but in more macroscopic, more granular matter scale of systems. So maybe one can also head to tail connect various hex bugs together and make a filament out of it and look at the dynamics of this. So what will happen in such a system? So what we see is that, but if you increase inertia, then you can see that beyond a point what happens is that if inertia is large enough, this will not get into that phase, and you see that this phase, the spinning active spiral phase, that region that decreases, that size of that region decreases as I increase, will get into the spiral, and at large enough inertia, this spiral again becomes unstable towards the open chain. So that's what happens. So I quickly show you. Yeah. So no, it's always there. Okay, so for example, so it's always there, but it's a question that how long it can spend in the spiral state. So that time scale, how long it spends in the spiral state, that decreases. So what happens is that if you look at the probability distribution of how much time it spends in the spiral state and how much time spiral state right-handed, left-handed, and how much time it spends in the open state. So this distribution will have 3 maxima, and the weight of this. Yeah, because these are all finite systems. So what will happen is that if you take the length scale of this filament infinity, then the lifetime becomes infinite. Once it gets into that, so if you do this finite size scaling, you'll see that the lifetime increases with the chain length. So that's why I'm calling that this is a phase transition. Okay, so maybe interesting is this lower one. The spiral forms because of the buckling instability, but how the spiral breaks is that suddenly this innermost region that turns back, and that turning back, the probability of that turning will increase the probability of the spiral, but that will just shift the boundary. Yeah. Okay, so then the other thing, let me just quickly just concentrate on this quantity. This is a Kullback-Leibler divergence between the end-to-end probability distribution of the equilibrium chain and the non-equilibrium chain in presence of this activity and inertia. So if you look at this quantity, what you see is that as a function of Peclet, so smallest inertia it increases, it shows some fluctuations here. But for the largest inertia values that I've shown here, you see that it increases, shows a maximum, and then comes back. Comes back, it's suggesting that at large, in the presence of large inertia, equilibrium-like behavior returns at large enough Peclet. So small intermediate Peclet, it becomes driven out of equilibrium, and then in presence of inertia, it becomes equilibrium-like at large enough Peclet. So we'll encounter this feature several times. So how much time we have? 10 minutes? Okay. 10 minutes before? 15 minutes. Okay, fine. So to summarize this part, that we have shown that active spirals destabilizes due to inertia, and at high inertia, activated equilibration-like behavior we see in the presence of larger Peclet. So we'll try to understand this. This behavior we'll see in other contexts as well. So this was the work done by Chitrak and in collaboration with Abhishek, who is in ISAR Mohali. Okay, so then let me go into active Brownian particles. The first look at the simpler parts. So simpler system is that, okay, so I can just think about a single active Brownian particle, ideal case, and then I can think about active Brownian particle in a harmonic trap. So we'll analyze this too, because for this too we can do exact analytical calculations. So how do we go about it? So if I mean this is the simplest idea, that the overdamped system, we are writing that in presence of, so what is happening, that there is a position, the position gets updated because of this active force, and the active force along certain heading direction, that's hat u, and there could be thermal noise on top of this, there could be some potential. But this orientation gets randomized. So as a function of time, so this orientation undergoes a rotational diffusion, and that rotational diffusion gives rise to this persistent motion of these particles. So in 2D, you can write it in this way. That was the overdamped thing. Simplest way to make it underdamped is that I'll use theta dot equal to some angular velocity and look at the dynamics of the angular velocity in presence of dissipation and fluctuation. And similarly for the in the presence of translational inertia, we'll do the same thing, that look at the velocity and evolution of the velocity. That's the simplest stuff. And okay. So the whole equations we can write down in terms of using these two characteristic scales, the persistence time scale and this length scale L, which gives you sort of the length scale over which the particle can diffuse due to thermal noise during the persistence time. So that's the length scale. So setting that these two together, you will get these 4 equations. So 2 equations for translation, 2 equations for rotation. So this can be in general present, but first let's take this perspective that we'll just look at the inertial effect in the translation. And rotation, I'll say that this is, since it's an active process, rotation is an internal process in which I'm deciding in which direction I'll go, and that may not depend on my inertia. So total body mass, maybe I reduce my body mass by 10 kg, but I can still make the same decisions. So I can ignore this part and just keep this theta dot as equal to omega and look at this this reduced set of equations and analyze it. So in presence of J, things becomes a little more complicated. If time permits, I can show you what it is, or after the talk, if anybody is interested. So with this perspective, one can write down these equations in general d dimension. So I can think about the motion of the particles in d dimension, and orientational dynamics happens in some other n dimension, and n can be equal to d or can be something else. So you can write down these equations. These are the Langevin equations, and of course straightforward to write down the corresponding Fokker-Planck equations, but it's not easy to solve these equations directly, the Fokker-Planck equations and the probability distributions directly. But what transpires is that it becomes easy that if we try to calculate the moments of the dynamics. So for that we perform a Laplace transform of these equations. This is the equation, and then write down an equation for a generic moment. So I say that psi is a function of all the dynamical variables, position, velocity, and the heading direction, and then you put this psi and can write down this generic equation for the moment. So this is the moment generator in that sense. And then one can go ahead and try to calculate particular moments for particular quantities of interest. Of course, for this system, quantities of interest are like velocity and velocity moments, position and position moments. So let me just quickly show at least one such calculation, how to go about it. So let's say that I want to calculate the second moment of velocity, so which will give me the kinetic temperature, for example. So to do that, one can set this psi variable equal to v square, and then I will also require a psi variable for the projection of velocity along the heading direction. So these two quantities, I put them back in the equation. So I'll get 2 equations, and then solve these 2 equations together. So I'll get an equation for the velocity squared in Laplace space, and this projected velocity along the heading direction in Laplace space. So these are these 2 equations, and note that both these equations have this generic structure. Their S dependence always comes in the form of 1 by S plus something and multiplication of those. So as a result, their Laplace transform will come out to be just exponential functions, and addition of exponentials, and what exponentials, that they will give rise to the time scales, particular time scales of decay of these modes. So this same method works for higher order moments, for example, v to the 4, etc., and position and orientation, everything. So that's number 1 point to note, and the number 2 point to note is the steady state is particularly becomes easy to calculate if I look at a quantity which has a steady state. For example, velocity will have a steady state for this free particle. For a particle in a harmonic trap, both velocity and position will get a steady state. So for them, one can calculate the steady state quantities, but just calculating the Laplace transform, multiplying it by s and going to s tends to 0 limit. Yeah. So I have a Fokker-Planck equation, then you write down moments, generic moments psi in terms of the probability, and then plug this moment into the Fokker-Planck equation, then you get an equation for the moments. No, so that comes if you look at a particular moment, when you start to calculate a particular moment, so it may or may not close in that level, right? So what happens is that if I keep up to linear order, so quadratic order in moment, in potential, so every calculation closes in that same order. So beyond quadratic, it will not. If either free or harmonic, these are two things I have calculated. So for them it closes, beyond it doesn't. Yeah. Okay, so going ahead, so I can, of course, simplest quantities would be the orientational correlation which we expect. This is a persistent random motion, so should show a exponential with the persistence time. So I have already used the time in the units of persistence time. So this quantity says that within a persistence time this will decay, the orientational correlation. So then one can do this for velocity, do this for velocity projection, and then come back to this lag function that I had shown that studied in this earlier experiment. So you can calculate that lag function, you get a closed form expression for that lag function, and which shows the same qualitative features. So we did not try to fit anything with here, so just showed that, showing that they have the same qualitative features. So this lag function starts with 0 and goes back to 0 beyond a time scale. Okay, so so similarly you can calculate second moment of velocity, fourth moment of velocity, etc., and look at all the crossovers and crossover times, everything can be analyzed. So and all these higher order moments in velocities, and so I'll not also stop there. Yeah, so the first interesting quantity in this calculation is the kurtosis of velocity. So if I look at this kurtosis of velocity, what one gets this exact calculation, and this exact form is plotted here. This is the heat map of this form, and this is a function of both this scaled inertia and Peclet number. So what you see is that in this form there are like this yellow regime is close to 0. Close to 0 means Gaussian like behavior of the velocity distribution, and corresponding distribution looks like that in 2D. And this region is where the kurtosis is strongly negative. Corresponding to that, the probability distribution looks like that. So it's a ring-like probability distribution. What you see is that here, with increasing inertia at a given Peclet, you see a re-entrant transition, that you increase inertia. First you enter into this non-equilibrium regime, then you again come back towards this Gaussian regime. So one can try to understand how it happens. Crossover, re-entrant crossover, yes. So how do you understand this crossover? The first thing is simple, that if I look at this m much greater than 1, this regime, in that regime what happens is that the persistence time, so m much greater than 1 means that the persistence time is much smaller than the inertial relaxation time. So by the time the particle forgets its inertia, it already has forgotten its persistence, orientation. So it becomes equilibrium like. 5 minutes to complete. Oops. So 5 minutes for question. Okay, fine. So this then what happens is that that's the simplest equilibrium-like behavior. So below that, if you come below that, what happens at the near m equal to 1, you enter this region in which these two timescales compete with each other, and below, as I go m less than 1, in that regime, of course, my persistence is dominant with respect to inertia, and because of that, I get this distribution which looks like this guy, with the peak of the distribution at given by the Peclet number one supplies. Okay, so that's understandable, but what happens below that? So in this regime, where you see that this is becoming further it's becoming Gaussian, that's the regime in which in the presence of that activity, you are decreasing m, and this size decreases, and then beyond this point, what happens is that the velocity fluctuation due to the thermal noise, that starts to dominate with respect to the velocity fluctuation. So as a result, you again go back to this Gaussian regime. So that's what happens here. So this is the cause of this reentrant transition. Okay, so I'll not say anything about that. Okay, so let me come to the steady state properties. So if you calculate the kinetic temperature of this system, you get this inertia dependence of the kinetic temperature. Effective diffusivity becomes independent of inertia. The swim pressure again depends on inertia and decreases with inertia. Kinetic temperature, you notice that it increases with inertia to saturate. Swim pressure decreases with inertia to vanish if inertia becomes really large. And the entropy production rate in this system, that also decreases with inertia. And final quantity we looked at is the violation of the equilibrium fluctuation dissipation, just looking at the effective diffusivity and the kinetic temperature, difference of that. So that quantity turns out to depend on this entropy production rate. So this violation depends. So it's understandable, we would expect that the violation of equilibrium fluctuation dissipation should be connected to the entropy production in the system. So it depends on this non-equilibrium entropy production. But this note that the non-equilibrium entropy production itself that decreases as a function of inertia. So this is again the same statement that I was making, that with larger inertia, activity sort of makes thing equilibrium-like. So inertial equilibration kind of behavior. A large enough inertia will get equilibrium-like behavior. So sort of inertia dominates and activity fails to keep up to the inertial time scale. Okay, so I'll not look at this trapped thing. Jump. So jump to the many body effects. So this part, this trapped thing part, these two things were done by Manish, and Manish has a poster. If anyone is interested, you can go to his poster. So then this last part was that active Brownian fluid at a density and activity, so that the system does not encounter the motility induced phase separation. So even in that level, what happens? What happens is that we can then calculate certain things. The velocity distribution, etc., has certain interesting feature. One thing one can look at is that interesting thing is that if I sit on top of an active particle and ask a question, what is the local environment? So this depends on which direction the active particle goes into. So environment in front and back are different. So there is more accumulation of particles in front than in the back. So this asymmetry is there for the overdamped regime. As you increase inertia, the amount of asymmetry itself decreases. So sort of, and the reason being that there is a collision from front and then there is a back collision. So it comes back, this collision and coming back, that feature was not available in the overdamped regime. So that's what is something which can sort of try to equilibrate the system. And another feature, interesting feature I would like you to note is that the effective diffusivity in this system, in presence of interaction, that guy depends on inertia. So we know that so over damped limit, what we expect the effective diffusivity should scale as Peclet square. So that's the scaling we get at small inertia level. But as one increases inertia, this exponent, or at least the apparent exponent, that decreases and decreases towards almost like linear regime. So that's one thing. So this exponent alpha d that depends on inertia, and as I increase inertia, it starts from the quadratic to almost linear. That's one observation. The other observation is that if I just fix the Peclet and look at the effective diffusivity as a function of inertia, so this guy decreases with inertia. So this property can be understood in terms of, so there is a argument that goes in. So if I look at particles in harmonic trap, there is a harmonic interaction, and in presence of harmonic interaction, even if I think about particles which are interacting with each other in a harmonic way, so particle can, if it collides with another particle, because the interaction is harmonic, it will penetrate that harmonic potential and stay a very long time. After that, it can come out. But if the interaction is hardcore like, so what happens is that if I increase inertia in such a system, it will spend more and more time at collision. But if I think about hardcore like interaction, what happens is that this guy at interaction spends very less time. As I increase inertia, it recoils and spends, like the time scale is extremely small. So these are this inverse of this time scale that gets into here. And with increasing inertia, since this guy increases, so as a result, the diffusivity decreases. But there is no completely analytic theory for that yet. And so in this system also, like we calculated the departure from the equilibrium fluctuation distribution, which shows decrease as a function of inertia. Again, for this many body system, we don't have a exact calculation like in the single particle. But this is the feature which sort of agrees with the behavior we have seen for at least the single particle level calculations. So this calculation was done by Shubhendu in collaboration with Fernando. So in this talk, what I tried to like behavior. So thank you.